And you think, well, how would they not have a pH of 7? Well, it depends on where they came from. They're going to do what? They're going to yank an H plus off of water, and we're going to get a little bit of this. Okay? Now, I'm looking for the pH. So if I could just find the concentration of hydrogen ion, and I hope you have a new appreciation for a salt after we've been talking about acids and bases. Now, remember where salts come from. If you take an acid and a base and you do neutralization, you will get a salt and water. Okay, so here are some examples what I mean by salts: magnesium chloride, calcium sulfate. Basically, they're just ionic compounds. Okay, and you think, well, how would they not have a pH of 7? Well, it depends on where they came from. It depends if there are conjugate acids or bases. So let's look for ions. Let's split these compounds apart into cation and anion, and then ask ourselves, are either of those going to donate or accept an H plus? That's the whole game right there. If they don't, then you'll have a pH of 7. If they do accept or donate H pluses, then they are acids and bases, and they will alter the pH. And so let me give you an example here. Sodium chloride is going to dissolve into sodium and chloride ions. Sodium, is it going to attract, attack water molecules, and is it going to form sodium hydroxide? Will it make a base? No, it's not going to do that. It's going to leave water alone. It's just going to be floating around as sodium ions. And so we'd have little sodium ions there. What about the chloride ions? What are they going to do? Are they going to attack water molecules and yank off an H plus? No, they're not going to do that, because hydrochloric acid is a strong acid. So these two ions are just going to be floating around, leaving water alone. They are not acids and bases. And so you would have a pH of 7. Now, what about fluoride? Take a look at fluoride. What does fluoride do in water? Could he grab an H plus and form hydrofluoric acid? Yes, he will. This is going to be in equilibrium. And so this is going to happen a little bit. Some of those little fluoride ions that are floating around in there are going to do what? They're going to yank an H plus off of water, and we're going to get a little bit of this. Now, when we get that H plus off of water, what's going to happen? Oh, we're going to have some hydroxides floating around by themselves. And so this is going to alter the pH of water. Of this solution. And so this solution would be a little bit basic. All right, so here is an example. This is ammonium chloride. So what are we going to have in solution? We're going to have ammonium, and we're going to have chloride. Will the chloride molecule attack water and grab an H plus? No, he's going to leave it alone. But look what we have here with ammonia. What does that look like to you? You can just see that he has an H plus that he just wants to donate. That makes him an acid, and he's going to donate that and make the solution a little bit acidic. So this would be a solution below 7. So here is a good example of this. We want to find the pH. We know the concentration. The first thing we need to do is write that reaction. We've got a conjugate acid here, ammonium, and we're going to write the reaction. And so when I write this reaction, I want to write the Ka for it. It's the concentration of ammonia times H plus, and then divided by the ammonium ion. Okay, now I'm looking for the pH. So if I could just find the concentration of hydrogen ion, it would be great. Now I know the concentration of I know the Kb for ammonia, and you say, well, this isn't ammonia, this is ammonium. I know, but they're related. So I don't know if you remember this, that the K of water, okay, which is 1 times 10 to the negative 14th, is equal to the Ka times the Kb. So if I want to find the Ka for a conjugate acid, maybe you don't find the Ka in a table, but you can find a Kb for the conjugate base. Well, it's kind of simple. We're going to find the Ka here is the kW divided by the kB. So 10 to the minus 14th divided by 1.8, 10 to the minus 5th is going to give me a Ka of 5.6 times 10 to the minus 10th. Okay, now there you go. Now I don't know these concentrations of the two ions, but I do know the concentration of ammonium, and that is 0.20 molar. Okay, so I've got that. That's the concentration of ammonium. Now, how much of that ammonium is going to give off an H+? Well, can we just say that it's X? Can I let X be the amount? And so my concentration here is going to be 0.2 molar minus X, and then our concentration will be X on the top for ammonia and also for the H+. We've seen this before where this little X right here is negligible. We've done this math because we have a really small Ka, and so 0.2 minus X is basically 0.2. This makes the math super simple. You're going to solve for X. We've done this before, which is the hydrogen ion concentration, and that is going to be equal to 1.110 to the negative 5th molar. Okay, now we're almost there. Remember what we were after. We're after the pH, okay, and so the pH, remember, is the negative log of the hydrogen ion concentration. And so pH is negative log of 1.110 to the negative 5th. That's going to be a really small number, slightly small, 4.98. Okay, and you're like, well, that is a salt solution. Why is the pH not 7? And why is it low? Well, what we have, one of my ions here of my salt solution, the ammonium part, look what he has right here. He's got an H+ ready to donate. Not all of them, just some of them. And so he's donating some H+, and that's going to drop the pH below 7.